Okay. Thanks, good afternoon, and thank you for having me. So this is a paper with Mahadev and Anand, who is at TH, and Anand is also at. So the central problem that we wanted to study here was what's known as quantum verification, which probably many of you already know about. So basically you are a classical computer, and somebody, Amazon or something, claims that they have a quantum computer. And you want to test whether it's the case, or perhaps you want to delegate some quantum computation to the server that you can't do yourself, but you'd like to know that the answer that they give you is actually correct. So one thing you could do, for example, is just ask them to factor numbers, right? We know that Shor's algorithm exists. And the good thing is that factoring is an NP, so you can check the answer for yourself very easily in that case. So, you can just ask, and then you can just multiply the factors that they give you and make sure that the answer is correct, which is efficient. But you might have problems that are in BQP, but not in NP. So there's a problem, for example, called correlation, which was introduced by Scott Aronson at some point. And it's just you're given black box access to two functions, and you have to decide whether one is correlated in some formal sense or correlated with the Fourier transform of the other function. Now it's not obvious how to check, even if the computer just tells you, what is the answer, it's you don't necessarily know if it's the correct answer or not. So the idea is that somehow this is often called like a classical leash on a quantum device. You want to have an interactive proof system by which the prover or the server, the so-called quantum computer, can quantumly efficiently prove to you that it's given you the correct answer. This is typically called a classical verifier proof system for BQP. No one knows if this object exists, but in 2018, there was a breakthrough work when Mahadev constructed argument systems for BQP, which means that instead of being secure against all possible provers, her argument system is secure against only computationally bounded provers under the assumption that learning with errors is hard. So learning with errors is like a standard cryptographic assumption similar to factoring. Hard. And okay, this is a very nice result. It was considered, a landmark result. Yes.
It's just the prover's computationally unbounded. You can do anything that you can do quantumly anyway, right? So.
Sorry?
If the prover is computationally unbounded,
yeah,
and you can do anything anyway that you can do quantumly, right? So.
Yes. Yeah. And including quantum. Yeah. So if the prover is unbounded, they can do anything. Here you're assuming that the prover is efficient, cannot do actually anything, just quantum efficient computations. Yeah. Okay, so this is a nice protocol, and all of the important parameters are polynomial. So the communication in the protocol is polynomial. The compute for both verifier and prover is polynomial. So for the verifier, it's classical polynomial time, probabilistic polynomial time, and for the quantum prover, it's polynomial quantum time, like quantum. But maybe you're lazy and you want it to be much easier for the verifier to do its job than in the previous protocol. So for example, you could ask, this is possible. We don't a priori know if it's actually instantiable, but it's a thing that you could ask. You could ask, I want the communication during the protocol to be polylog. And I want also the compute to be polylog. Now that's not exactly possible because you have to read the instance at least, right? So you can just throw in like an O tilde of n, and that will allow you to read the instance, and then all the work on top of that, you say, I want it to be polylog. Like O tilde of n, or O of n is like basically the least possible work you could do in order to read the instance.
Sorry, what is lambda?
Lambda O, good. So lambda is the security parameter for the crypto. It's usually denoted by lambda is separate from n because you might want the lambda not to be polynomially related to n. Yeah.
The compute here is the compute of the quantum computer, I guess, not of the classical.
No, the compute on this side, the left side, is the classical verifier's compute. The compute on the right side is the quantum computer's compute, which remains the same. It's still polynomial.
There are problems that provably take quadratic time or cubic time and anything super linear, right? By the time hierarchy theorem.
Yes.
So somebody somewhere here has to do like quadratic work. Okay.
So you might ask for this, like you don't know if a priori if it's instantiable, right? But it has a name, it's called a succinct argument. Earlier I said the Mahadev was an argument for BQP, now this is a succinct argument for BQP. And just to familiarize ourselves with the landscape, in the classical world, this object is an object of study. And there it's a little bit different in that, well, it's the same idea. It's like your weak classical computer, and you have access to like a powerful server who does computations for you, and you want to check that they're correct. And you don't want to do as much work as you have to do to actually do the whole computation to check the answer, right? That would be pointless. So the point is you should have a succinct argument where the communication is polylog in the time that it takes to do the computation. The compute is O tilde of n because you have to read the instance, and then plus polylog of the time it takes to do the computation. And the compute for the server is just like poly of the time it takes to do the computation. Now, it's a little like, you're supposed to imagine here that t is exponential in n, because why would you delegate the computation if it was very easy, right? You would possibly only want to delegate it if it was very hard. So if it was like much more powerful than you. So that you can't just like take this and apply it to quantum to get a succinct argument with these parameters, because naively, like quantum algorithms take exponential classical time to run, and this protocol, whatever it is, it runs in time polylog for the verifier. It runs in time polylog in the time it takes to run classically the computation. So that would be polynomial if t were exponential. So it doesn't translate automatically. In fact, you can see by this that like this object is actually quite strong. Like you're asking for something that would naively not be achievable like these classical protocols. But you're just hoping that because it is an efficient quantum algorithm, that somehow you can do this. Does everything make sense so far? Any questions? Okay. Okay, so this object was known to exist in 2022. But the main catch was that it was only known to exist assuming post-quantum IO. So IO stands for indistinguishability obfuscation. It's a very strong cryptographic primitive. Yeah, I have a slide. Okay, so it's extremely powerful because IO and one-way functions together imply almost every known primitive. So we all know about the standard landscape, hopefully. Maybe we don't actually. Some people here are not cryptographers, but so in crypto, there's in classical crypto, there's law that says there's one-way functions, which imply almost everything that we know. And then there's public key crypto, which is kind of separate. One-way functions do not imply public key crypto. And public key crypto implies almost everything else that's common, except the newer, like more powerful things like homomorphic encryption, things like that. And but IO implies basically every primitive that we know. If you for some reason IO by itself does not necessarily do so, but IO plus one-way functions are considered to be very basic, and you need them for any crypto that exists at all. If you have IO and if you have one-way functions, you basically have everything, like public key crypto, homomorphic encryption, like anything you can think of. Yeah. And so for the first time in 2022, JLS constructed IO from a set of standard assumptions. So before that, it was all like heuristic constructions. No one really knew if it would be based on like factoring or LWE or anything like that. Now in JLS, in their 2022 paper, they constructed it from 4 assumptions. It's usually it's like, oh, you can pick one and it's like it will work, assuming that one is secure. No, this one you need to assume like 4 standard assumptions are secure. So we have LWE, learning with errors, we have learning parity with noise, we have PRGs exist in NC0, and we have this thing called SXDH, which is like a more stringent assumption than DDH. So decisional Diffie-Hellman. Okay, so these are 4 standard assumptions. People use them and they're considered to be secure. So that counts as a construction. It was a major problem. But SXDH is not post-quantum because it's a version of DDH. And we know that quantum computers can break factor. So we do not have any standard construction of post-quantum IO as yet. And in fact, if we did, it would imply other very elusive cryptographic primitives like public key quantum money, if you know what that is. So it's something that you don't really want to use until someone maybe invents like a construction, right? Because also it's just like a huge hammer. It's not clear if you actually need it. Is all clear? Okay, great. Okay, so we can look into a little bit why this was necessary, right? Why do we need to use IO? And the reason is sort of the structure of Mahadev's original protocol for verifying BQP computations. So if the history state of the computation, in the Feynman-Kentaev sense, right? If the history state has 5 qubits in it, for example, then you need 5 keys. So basically her approach, like, okay, how do you verify that someone did a computation correctly? One way is just sort of force them to do all the computations that are involved, you know, step by step, right? Somehow using crypto. And okay, she has a way to force the prover to do X basis measurements or Z basis measurements, and to definitely check if they did something else. Like they have to do that or they won't pass the protocol. She calls it like a simulated measurement device or something. And the way she does it, she just sends 1 key for every qubit in the history state. And each key sort of determines secretly which basis is supposed to be measured for that qubit. And the prover does not know which basis, but the verifier will know because they sample the key. So you need 1 key for every qubit. So that's already like Pauli number of things that you need to send the prover, right? So you're never going to get, well, unless with much difficulty, you're not going to get succinctness this way. And then there's some answer from the prover, and yeah. So the way BKL, etc. do it is that they use IO to compress the keys. So it turns out that the answers from the prover can actually be compressed relatively easily into a succinct, you know, to get answer succinctness in the crypto world is relatively easy. You just use like this Merkle tree trick, basically. To get succinct questions is hard, and they do it using IO. I don't actually know the details because it's complicated. It's like IO is one of those things where like 5 people in the world know how to apply it. Vinod happens to be one of the 5, so that's what they did. Yeah, so that's the reason they have to use IO, because fundamentally Mahadev requires 1 key for every qubit. And then they just like somehow cleverly compress the key sampling into like a program that they can then obfuscate using the indistinguishability obfuscation. Okay, so yes.
Basic question. What does IO indistinguishability obfuscation? What does it do to the basis?
What does it do to the basis? Like, what does it do to
the X and Z values? What?
Okay. Okay. Maybe I should just say briefly what IO actually is, or maybe you want to say like. Okay.
It's a classical thing. No?
Yeah, it's a classical.
It's not a.
Yeah, it's a classical primitive. Exactly. Yeah. So like, it basically like okay. You know how like maybe software companies, they have like some code that they developed over many years and they want to like keep it secret to prevent people from like, you know, using their code because it's like their intellectual property, right? That like if they have some proprietary software, they might want to have a way to like obfuscate the code to just like the code will run if you get it as a program, but there's no way to like, and you could copy it because it's classical, right? But there's no way to like reconstruct anything about its internal structure, very hand-wavily speaking, by just looking at it. Like intuitively, it should just act like as a black box where it gives you the right outputs and inputs, but you cannot actually know anything about how they implemented this program. Yeah. So that's what IO is supposed to do. It doesn't actually do that because that's impossible, as it turns out. The IO is like the best possible alternative to this. Okay. So we want to build succinct arguments for QMA. And we want to get around this roadblock that, yes, yeah.
So in this protocol that you described, you are able to compress the choices of X or Z bases into a smaller size.
Yes. So the way they do it is, it's pretty magical, but IO is very powerful, as I said. The way they do it is they just, so instead of sampling uniformly at random, they sample from a PRF or something. And of course, you can't just like do that. Like you can't just give the, okay, there's a short program describing how to sample keys from a PRF, right? Now, you can't just give that to the prover because they will just look at the program and like know what would come out, right? So that's why you need obfuscation. So you like make that program and then you obfuscate it and you prove that the prover cannot like learn anything about how the bases are actually distributed based on your program.
Okay.
That's a good question.
Yeah.
How interactive is this? Like your picture suggests one message one way, one message the other. Is that it, or is it multiple rounds of communication?
I think it's like 3 messages or something, maybe 4. They're not too, okay, actually, never mind. There's like this second step is very interactive. So it's like 12 or something, counting the second step. The original protocols like can be done in 3 or 4 steps. There are also non-interactive versions with quantum random oracle. Questions? So the problem we want to solve here is we want to get succinct arguments and we want to not use IO, right? Because no one knows if it actually exists relative to post-quantum assumptions. So how could we possibly do that? Well, we just need to use a verification protocol with a different structure. We need it not to be qubit by qubit, right? So what verification protocols with the structure exist? Well, as I said, verification is a fairly new primitive. The first time someone ever constructed it in the sense of like cryptographically sound protocols was 2018. But there is one other approach that's like substantially different. And so, okay, before Mahadev's work, you know, hers was the first work in the like cryptographic standard model, but other models were known to have verification protocols before her work. In particular, it was known to be possible in the MIP star model. So instead of you being a classical computer and interacting with a single quantum prover and wanting them to prove to you that they computed the answer correctly, you could interact with 2 provers who are allowed to share entanglement. I mean, it's just like that. Like, don't ask me why the model is like this, but it's like an interesting model of study. And it turns out that you can, in fact, force the 2 provers, if they share entanglement, to prove to you that they have done the computation correctly, right? 2 meaning like why can 2 just not be combined into 1? Because the stipulation is that the 2 provers, after they receive your questions, cannot communicate among each other. So they have to answer your questions. You'll reject them if they answer wrongly, but they can't like collude by communicating. They can share entanglement, but they can't, you know, actually talk to each other. Okay, so the question that was open even before Mahadev's work was, can you somehow like convert this 2-prover thing into a 1-prover thing by compiling it in some sense? I mean, I don't know what the definition is at this point, but you know, that would be a nice thing to have, right? Just like compile the 2-prover thing because we already know how to do that. Okay, so I guess I said some of this already, but just to recap, the classical MIP model is, you know, another model of interest in complexity theory. More precisely, like, again, as I said, you are a classical verifier, you interact with 2 unbounded provers or servers, whatever you like. You send them questions, 2 questions, 1 each, and they give you answers. And then you like do some computation on their answers and decide whether you accept or reject them. In this model, in the plain MIP model, they're not allowed to even share entanglement. They also are not allowed to communicate. So in complexity theory, this corresponds to a complexity class, which is defined by the things that, like the computational problems that you can decide after interacting with these 2 all-powerful provers in this way. So, you know, formally would be that. I won't read it out loud because we can all read. But the problem with the MIP model in the crypto setting is that, you know, how do you enforce the no communication assumption, right? Like usually in crypto, we're actually trying to defend ourselves against real world attacks. And that's why we use computational assumptions, supposedly, right? Because we assume that no one can break the computational assumption. If they did, they would be like very clever and the algorithms people would be happy. So, I mean, one way that you can actually implement the no communication in practice is to ask them to answer you very fast. Just put them very far apart. So like light does not have time to travel between them before they have to answer you. Like if you put yourselves in appropriate positions, this is possible. But this is like very annoying, right? Now you have to like make sure everyone is in like appropriate locations on the earth or something. And also, what if the computation just takes a long time? Then you can't really ask them to answer you very fast. So however, I mean, why would people care about this like very artificial model at all? It's because there are very many useful techniques in the MIP model that don't necessarily translate very easily, like obviously to the cryptographic setting. And, you know, they provided the springboard towards like the proof of the PCP theorem and stuff. And maybe you just like want to use these techniques, like you want to somehow imitate them because they have very good ideas. So one thing you might want is a compilation procedure, as I said, which takes any MIP proof system, converts it to a single proof of protocol while preserving completeness and soundness. Completeness and soundness, as I said, with these properties. So you have some instance that you're interested in deciding if it's in the language or not. It should be that, like, if the instance is in the language, then the provers there will be some provers who can convince you of this fact. And if the instance is not in the language, then no provers, even unbounded ones, can convince you using the MIP protocol.
Can I ask a question on the previous slide?
Yeah.
So the last bullet, I mean, MIP is a much bigger complexity class than one prover classes like NP and MA, right? So surely the last bullet is not possible as stated, but you're probably implicitly assuming.
No, it's not. You're right. Okay.
So are you assuming something for the single prover protocol, like just cryptographic soundness or something else? Or?
That's a good question. Like a priori, okay, it's like you assume crypto.
Or maybe the compilation procedure doesn't have to be efficient. Is that it?
It is efficient. But the thing is, you assume the crypto holds against the provers. So okay, to be clear, you won't get a proof system out. You will get an argument system. It's only sound against a computationally bounded single prover. Yeah, so I guess it's not a complexity statement that we're looking for. It's a crypto statement. Does that help?
Yeah.
Okay. Okay, so the only cryptographic primitive we need to do this, as it turns out, is called homomorphic encryption. It's a very easy primitive, a natural primitive, I think, to state what it does. To actually get it is hard. I think it wasn't known until 2009. It remains only known from LWE, like there's no factoring-based assumption, factoring-based instantiation. But it's a very natural primitive. It's just very powerful. So the central point of homomorphic encryption is to allow you to compute on encrypted data. So a normal encryption scheme has two algorithms, okay, three, like a key generation, encrypt, and decrypt, right? A homomorphic encryption scheme also has those three algorithms. It has algorithms, and it has one more called eval, usually, which it takes a ciphertext and a public key, and then a function. And it computes like some function on the encrypted ciphertext. So it should be that like, after you imply eval with some function, you get out the encryption, like let's say the original encryption that you had encrypted some message called X. After you apply eval with some function F, let's say, you should get out the encryption of F of X. So you sort of are computed under the encryption. This doesn't violate security because you don't actually know what you're computing on. You just know that you evaluated some function, and you can't actually tell what the output is or what the input was, right? And so you don't need the secret key in order to run eval. Right? That's supposed to be the main magic property of homomorphic encryption. Oh, maybe I should just pause here. Does anyone have questions about homomorphic encryption? Okay. Okay, so one way that you might try and, so the idea that we want to exploit is that you have this two-prover system, which was just handed to you. You know that it's complete and sound in the two-prover world, but you can't enforce this no communication assumption, right? So you want to make it into a one-prover protocol, and to do that, you have to somehow like cryptographically simulate the no communication assumption between the two original provers, right? So one way you might try to do this with the homomorphic encryption primitive is as follows. Originally you would have sent two questions, X and Y, to the two provers. Now you just have one prover. So you could send both questions to the same prover, but that is clearly insecure because now the prover knows both questions, right? And they can obviously cheat. And the original protocol really relied on like one prover not knowing the other prover's question, for example. So what you could do is encrypt both, right? Encrypt both questions and send them both to the same prover. Okay, now it's kind of useless if you just use a normal encrypted scheme. It's kind of useless because now they just have like two random ciphertexts and they don't know what to do. Like they don't know what the questions are, so they can't like, indeed they can't cheat, but they also can't like help you, right? So that's why you should use homomorphic encryption, because what is homomorphic encryption? It allows you to do computations on the encrypted data. So there was some circuit that the original provers, let's call them Alice and Bob, because that's standard. There was some computation that Alice, the prover on the left, let's say, would have done to convert X, your question, into A, her answer, right? Now, homomorphically, if the prover receives an encryption under some key of X, they can just homomorphically compute an encryption of A. And similarly with the other ciphertext. But the magic is that somehow they don't actually know what the questions are. They're just blindly computing this function that original Alice and original Bob would have computed. So they cannot cheat, maybe. That's sort of the intuition that you'd hope for, right? But they will be able to help you. They will be able to compute, just blindly compute that. That make sense?
And so,
Yeah.
like, the reason you're using two keys is because if you use the same key, then they could try to simulate the communication somehow.
Exactly. So if you use the same key, that's a great question. If you use the same key, they can homomorphically, like, let's suppose they came up with a cheating strategy before you sent them the stuff. If you use the same key, they can homomorphically execute the cheating strategy. Yeah. But because it's different keys. Yeah. Questions? Yeah.
We also homomorphically combine the two encoded answers if they are encoded under different keys, like computing A plus B, for instance.
Not under different keys. Like different schemes with different keys are just completely like separate. Yeah. Okay, so that actually doesn't work. Like this compilation fails in a sort of interesting way. And we understand tightly, in fact, the properties of this compilation. It preserves non-signaling strategies. So I won't define what that is, but it's basically, so okay, what we wanted here was to preserve classical soundness and completeness, right? What this compilation turns out to actually do is preserve non-signaling completeness and soundness. So non-signaling strategies are a class of strategies that are more general even than quantum strategies. So, okay, we sort of failed to do what we wanted, which is preserve classical soundness, because, you know, just because classical provers cannot cheat doesn't mean that there are not non-signaling provers that cannot cheat. There's still some restriction on what the provers can do, but non-signaling is a more general class than classical. So, and in fact, you can instantiate any non-signaling strategy. This was shown by DHRW in 2016. That's very non-trivial. It involves, like, for particular encryption schemes that are homomorphic, you can construct a strategy that instantiates any non-signaling strategy, which is kind of surprising. Okay, so you can already do delegated computation in the classical case here because non-signaling MIP, as it turns out, is equal to X. So if you wanted to do any computation that lies in X, you could use this compilation model to do it. And that's, in fact, the original motivation that KR14 had to study this. But okay, that's not what we wanted. So. Questions? Is this clear? Okay, so let's try again to get what we wanted. This is due to KLVY, so Kalai, Lombardi, Vaikuntanathan, and Zhang in 2021. So Okay, what did we do that's different from the previous picture? Nothing, except that now I'm going to the verifier is going to send the encryption of X to the prover and then ask immediately for the answer back. Under the same key, homomorphically as before, and then only send the encryption of the second question and get back the second answer encrypted. So, I mean, this doesn't look very different, right? It's almost the same. You just sort of split up the rounds. The thing is, the strategy that could simulate non-signaling strategies from 2016, it really crucially relied on being able to have both ciphertexts at once. Even if you couldn't read them, somehow having them together allowed you already to do something. So here you can't, right? You have to answer the first one before you get sent the second one. And in fact, if you think about it for a second, if it's not obvious, it's fine. But maybe you can see that, in fact, you don't even need to encrypt the second pair in this situation. You can just send them in the clear because once you're at the second round, the second pair of messages, the first round has already been dealt with. So you don't really reveal anything extra by not having the second round to be encrypted. Again, it's something you have to prove, right? So if it's not obvious why, it's fine, but it just makes it notationally simpler to think about it that way, right? So that actually works, as it turns out. This preserves classical soundness, as KLBY proved in their paper. And it sort of obviously preserves classical completeness if you have the right homomorphic. Right? But then we might ask, what about quantum soundness? And okay, I want to, what do I mean by quantum soundness, right? I said a little bit about MIP star, but let's just make it more explicit. So what is MIP star? It's the same as MIP, except that you have this entangled state. Okay, you have some, apart from not being able to communicate, the provers can share entanglement. That doesn't allow them to communicate, of course. That's something that they were not allowed to do in the MIP. So what does it mean to share entanglement? It means you have some global state psi, which may be entangled. And then Alice, the first prover on the left, keeps half of it or some part of it. And Bob, the second prover, keeps the other half. So they just take this entangled state and then just take the qubits and split them apart and then go to their separate rooms or whatever where you can ask them the questions. Yeah, so they hold the state and they can possibly use do measurements on their states as well as computations about your questions in order to answer your question. So that's the MIP star model. And okay, you can also ask to compile this. Yeah.
Maybe a naive question, but what do we actually know about MIP with shared randomness? It's just MIP. Or?
It is not just MIP. How many people know what it is? What its complexity characterization is? Come on, Okay, so maybe I can do a show of hands. Who thinks it's larger than MIP? The reason you might think this is that having entanglement might allow them to do stuff for you that they couldn't do before.
What are you asking about?
What is the complexity characterization of MIP star?
Oh, okay.
The question was shared randomness.
Shared randomness.
Classical random.
Yeah.
Oh, shared randomness. Okay. Not actually sure. My intuition is it's not equal to MIP star. The fundamental power of MIP star comes from the fact that you can not only have shared randomness from the entanglement, but verified. You can check, you can force the provers to honestly give you use their shared randomness.
There is a comment, Randy.
Thanks.
Yeah, that is potentially the case. I'm not actually sure it's proven, but I would.
No. You could think of MIP with shared randomness as just the mixture of different pairs of provers.
Sure, yeah.
And if you have the right soundness and completeness without a shared randomness, then in the yes case, there will be a good pair of provers. And in the no case, nothing in that mixture of pairs of provers will have a large acceptance.
Yeah, this proves that MIP with shared randomness contains MIP, right? It doesn't prove that they're equal.
I think that should show that they're equal.
Why? Because like, okay, you just proved that any MIP protocol will translate to an MIP with shared randomness protocol, right? But
No, but
You're saying-
conversely, suppose you have an MIP protocol with shared randomness, then in the yes case, there will exist sort of a shared randomness prover pair that has high acceptance probability. Now, one thing in that convex combination will be an unshared randomness pair of provers with high completeness, high acceptance probability. And conversely, like if no uncorrelated pair of provers has high acceptance probability, then no mixture, no shared randomness combination will have high acceptance
okay,
probability
yeah,
either.
Yeah, that
That's
makes
what Randy saying.
Yeah, exactly.
yeah, okay, so I guess that answers your question. Yeah.
And MIP star is RE now, right?
Yes. Oh, yeah, I feel that it didn't finish the, yeah. The MIP is equal to next, MIP star is equal to RE. Like it contains and is equivalent to the whole thing. Okay, so we might want to compile MIP stars. And maybe I said the motivation many slides ago, but like, just to remind ourselves, like, the reason is that we know how to do verification in the MIP star setting, right? So it was known before Mahadev's working, but so if we could just like take that to prove a thing and make it a one proof a thing, we would get a verification protocol. And okay, why do we want a verification protocol? Mahadev already had one. Well, one reason is that it's nice to have different proofs of the same thing, right? Like think of the QPB theorem. The other reason is that it might be, maybe we'll have a nicer structure. Like Mahadev's thing really relied on this qubit by qubit approach. Maybe if you do it this way, you'll have, I mean, of course I'm saying it with hindsight, right? But, you know, maybe if you do it this way, you will have a nicer structure that doesn't have a qubit by qubit sort of framework. Okay, so we try to compile MIP star. And you can just do the same thing. Like this actually makes sense in the MIP star too. And okay, maybe you're a little bit worried about like what happens to the shared entanglement under the homomorphic encryption. So remember I said you had to like homomorphically compute A from X, right? Well, originally, like in MIP star, Alice would have done some computation that involved both her shared entanglement qubits and your question to get A, right? And she would have done some measurement on her shared entanglement that was also correlated with your question, right? So if it turns out just if you have a quantum homomorphic encryption scheme with strong enough correctness, then this, like you can do all of that homomorphically, you can like encrypt the Alice can by herself because it's public key. Like homomorphic encryption is always public key. Alice can encrypt by herself half of the shared entanglement, and then she can homomorphically do whatever thing she would have done on the shared entanglement and your question and get out an answer that's encrypted. Like a measurement outcome that's encrypted, which happens to be a ciphertext, and just send it to you. And if the correctness is good enough, this will preserve the shared entanglement with Bob. Right? So that satisfies completeness, in fact. This scheme satisfies completeness. Oh yeah. Oh, maybe I didn't say this already. I forgot. Okay, well, that's what I just said before. So we already knew how to do it in the two-prover model. So we wanted to like do it in the single-prover model by compiling. And quantum homomorphic encryption was also known. She, in fact, Mahadev developed it herself. She couldn't see how to like make it into a verification, but that's what Anand and I did in 2023. So we showed how to use KLEY compile a two-prover protocol in order to make a single prover verification and just recover Mahadev's work. Now, why did we have to do that? Like, you know, didn't KLBY already show that? And they didn't show any quantum soundness properties. So there was no guarantee that applying the thing to a quantum, like they had the quantum application in mind, but they could only show quantum completeness. Like they didn't know how to show quantum soundness. We don't know how to show quantum soundness either, but we showed it for like CHSH, and that it turns out is good enough if you want to compile a verification. Now this is nice. Our protocol from 2023 is non-succinct, but any compiled protocol only requires the verifier to send the prover a single key, right? It's just the key of the homomorphic encryption scheme, that's it. And then you have like these messages, but they're not qubit by qubit. They would be, if you had a succinct MIP star protocol and you ran it through the compiler, the output would also be succinct, which is really nice, right? Because that seems to just solve the problem for us. You'd hope, at least. So the compilation of a succinct verification protocol in the MIP star land is already succinct in the one prover land. So you might just hope to get succinct verification by taking a succinct verification protocol in MIP star land and passing it through KLVY. But succinct two-prover verification doesn't exist, as it turns out. Succinct two-prover just meaning like the communication is log, polylog, and the verifier's compute time is polynomial, as you know, with the one prover set. Sorry, the verifier's compute time is polylog plus O tilde event to actually read the instance. Okay, so why does it not exist? Here's what's known. This was me and Anand in 2022. Succinct MIP star, so with short communication, with polylog communication, contains RE. So, you know, it definitely contains BQP. But this requires inefficient provers. And even if you specialize to BQP, the provers do not become efficient. Like they still are like classically inefficient. Okay, so that's not useful. There was a claim that succinct 7-prover MIP star contains QMA, which contains BQP, with efficient provers. This was in 2018 by Anand and Tamar Videk. Unfortunately, there were 2 mistakes in this proof, one of which has been fixed by MIP star equals RE, and one of which remains unfixed. I think Anand and Chinmay posted a note about the remaining mistake. Also, no one wants to deal with 7 provers, so you know, this is nice, but like, okay, it's wrong and it's very inconvenient. So, okay, so maybe you want to like look a little more into all this magic that they did for MIP star equals RE to see if there are like useful techniques you can pull out. And in fact, they have these things called compression theorems, which Randy introduced at Q-Lunch. So question compression makes the questions in a non-local game shorter. So you take a non-local game, you pass it through this thing called question compression. It's the proof technique. And it gives you like a non-local game with almost the same properties, but the questions are much shorter now. And answer compression does the same thing for answers. So why are you just like done already? The answer is because it's like answer compression is complicated is the answer. So despite like they're both like trying to achieve the same objective, sort of, but question and answer compression are very different. So the best question compression is based on like this question efficient Pauli grading test, which was developed by Dolasal in 2022. And so the original Pauli grading test samples questions from 0, 1 to the n. If you want to Pauli test n qubits, and if you don't know what that means, it's fine. And the question efficient version just comes from like sampling these questions from epsilon bias sets instead of from the whole space. It's very easy. It's very simple, and the analysis is not even, it's actually quite neat once you read it and understand it. However, answer compression, the best one is based on quantum sound PCPP, so PCPs of proximity. And this analysis is very delicate. To this day, we don't know how to make a compiled version of this analysis, which was, I don't know, it involves like, I won't get into it. There's a step which Anand and I call the magic SDP, because it's just like you take the strategies that you were using and you want them to be better. So you just like find an SDP and like stick them in to the SDP, which spits out some new strategy. And then you use duality to argue that it's better. And even Tamar, I think, has no intuition for this, but he was the one who came up with it. So, okay, so there's that. And there's also the problem that there are stringent conditions about when you can actually use answer compression. And unfortunately, there is no 2-prover verification protocol with efficient provers that satisfies the conditions. So, okay, that's kind of, you know, a bummer because you can't use answer compression now. So, okay, we still don't know if there's a succinct verification protocol with efficient provers that can decide BQP. That is, in fact, basically the quantum games PCP conjecture. It has really nothing to do with the Hamiltonian PCP conjecture, but I guess Tamar decided that it should be called the games PCP, so that's the name it has. Okay. However, recall that in the two-prover world, I just said that question compression is like easy in that now we understand it really well because people have studied it a lot, and it turns out that you can do it with simple tools. And answer compression is what remains hard, right? So remember also that in the cryptographic world, you know, the opposite, like questions could only be compressed with difficulty using IO, and the answers were somehow easy to compress because you could, in that setting, you could just use hash functions. And like commitments, like succinct commitments, which do not exist information theoretically, right? There's no way you can compress a commitment in that way, information theoretically, but you can do it with crypto. So, okay, so why don't we just combine them, right? Somehow we want to use the two-prover question compression and then use cryptographic answer compression. And that's exactly what we do. So we use the two-prover question compression in order to get a question succinct protocol. So this is all in the non-local world. And then we compress the answers and the verifier running time, as it turns out, can also be done cryptographically, just using the sort of hash function approach. So that's basically the roadmap of how we got the results.
Sorry,
Yes.
one question. Like you said, this answer compression was very difficult, but it's because question compression is possible and it's not so delicate, or
Yes. Yeah, good question. So question compression is not so delicate, and it also happens to apply to like known two-prover verification protocols. So like answer compression is difficult to compile for two reasons. Firstly, because we don't know how to compile the analysis. Like when you compile something, like there is no general soundness result known for compilation, for KLVY compilation. So if you want to compile something, you just have to like redo the analysis, but like in the compiled setting, keeping track of all your crypto stuff. There are certain techniques that we know how to do in the compiled setting from the non-local setting, and certain ones that we don't. And answer compression is like the one very interesting game I can think of where we don't know. There was recently a general result that said that like KLVY actually preserves quantum soundness if you take the security parameter to infinity. But so this says like as you take the security parameter infinitely large, the adversary's cheating probability becomes 0. But this is not cryptographically useful because you can't tell what you should set your security parameter to in order to get the right soundness, right? Yeah. Does that help? Okay. Okay, so I wasn't sure how much time I'd have and how many questions I'd get. So I have, you know, that's the end of my slides, basically. I can also explain, there is time, how you actually get question succinctness in the two-prover setting, because I think it's kind of nice. But maybe I'll just say the open question. So the like easy open question, maybe that like should definitely be doable open question is like you can try and just use this approach for more things, right? Like for example, one thing you might want. So in this protocol, I said that the prover's runtime was just any polynomial, right? In n and lambda. You might want it to be more efficient than that. Maybe you care about like the server's compute time too. And so you want it to be like linear time, maybe, which is the shortest it can possibly be. So somebody constructed like one prover quantum verification from cryptographic assumptions that was linear time for the prover. Unfortunately, it used a quantum random oracle, and also the paper is like 120 pages long, and I think no one understands it apart from the author. But there's possibly a way to get it without the random oracle, which is like to prove a linear time verification is known. It's like this paper by Andrea and others from 2017 or something called Verifier on a Leash. So you could try and just compile that. It might work, right? So, and I think it probably would if you spent enough time doing it. Unfortunately, the 2017 paper is already a bit complicated, but at least you have a guiding, like a starting point. And then like more open-ended, less rigorous questions, like, okay, can you somehow like do this in other settings? Like, can you take cryptographic techniques and like combine them with two-prover techniques? It's an obvious open question, but I don't really, like, I have no inroads, I guess, apart from the first thing. And maybe also like, so far it's mostly been a matter of self-testing techniques being useful in the crypto world, right? Because you have all these techniques from MIP STOC, and then you want similar things in the crypto land, and then you just compile in order to bring them over, right? But I don't know, maybe techniques in crypto can also inform self-testing. Like there's this remaining open question, quantum games PCP, which is just to like design a two-proof verification protocol, basically, that is efficient and that has succinct questions and answers. Because since Tomas and Anand's paper was discovered to be broken, no one knows how to do this. And indeed, the hard part is answer compression in the non-local setting. And I'm unsure how much this cryptographic answer compression can inform techniques there because of the reason I stated. Like information theoretically, you can't use this like Merkle tree kind of approach. But you know, in a very vague and open sense, like possibly we could learn something from crypto self-testing world. Okay, what is the time?
Yeah, 5 minutes.
Okay, yeah, okay, so maybe I'll stop there and this questions.